In this section, we talk about deep repetition learning for causal inference. First of all, deep learning architecture is one of the popular methods during those years. Deep learning architecture is composed of an input layer, hidden layer, and an output layer. The output of each intermediate layer can be viewed as a representation of the original input data. They are able to deliver high-quality features and enhances the learning performance. The representative examples of deep learning architectures are feed-forward neural network, convolutional neural network, CNN, autoencoder, variational autoencoder, VAE, generative adversarial network, GAN. In this section, we'll talk about three kinds of deep representation learning methods for causal inference. There are balanced representation learning, local similarity preserving based method, and deep generative model based method. The first one is a balanced representation learning method. It views the counterfactual estimation problem as a domain adaptation problem. In detail, it contains two domain adaptation problems. The first one, the source is the observed treated features or treated covariates xt, and the treated outcome yt equals 1. The target is a counterfactual outcome of the treated control group, that is the treated outcome of the control group. Similarly, the other one, the source is the control feature or control covariate xt, and the control outcome yt equals 0. The target is the control outcome of the treated group. The goal of balanced representation learning is to project the original feature x to a new space so that in this new latent space, the treated and control groups are balanced, which means the two groups, xc and xt, has more overlapping in this space. And then the outcome prediction are made based on the balanced representation space. On the theoretical background of the balanced representation learning for causal inference are that the expected error of ITE estimation comes from two parts. The first one is the expected supervised learning generalization error, and another one is a distance between the treated and control group in the representation space. Based on this theoretical result, a series of work has been proposed. The first is a BNN. The figure shows the framework of the BNN. The red blocks are representation neural network, and the regularization is applied on the learned representation phi to minimize the distance between the treated and the control group in the representation space. After obtaining the representation phi, it is concatenated with the treatment scalar t. The concatenated vector is then fed into the prediction network marked as blue to get the outcome. Based on this, the objective function contains two parts: the factor loss and the discrepancy of the treated and control group in the representation space. The next is the counterfactual regression, shorted as CFR. It's kind of similar to the BNN, but they're different in that the representation is no longer concatenated with the treatment T. Instead, in CFR, the authors designed different prediction networks for different treatments. The reasons are that in BNN, the representations are usually high dimension, while the treatment T are only one dimension. In this case, the effect of the treatment may be overwhelmed by the representation vector. That's why the authors designed different prediction networks for different treatment. Similar to Bn, the objective function contains the similar two parts, the factor loss and the discrepancy regularization. Next is the experiment of Bn and CFR on IHDP and job dataset. On IHDP dataset, as it has ground truth treatment effect for ITE, the evaluation matrix is a precision in estimation of heterogeneous effect PHE, which is the IMSE of the IT estimation. For ATE, the absolute error is adopted. On jobs dataset, because it then has a ground truth ITE, the policy risk is adopted, which is the average loss in value when treating according to the policy implied by an IT estimator. For ATT, the average treatment effect on the treated group, it has the ground truth, and similar to IHDP dataset, the absolute error is adopted. All those evaluation matrices are the lower, the better. Here is the result under the within sample case. It estimates the IT of the unit whose outcome of one treatment is observed, and it is evaluated on the training data set and the validation set. The right table shows the results. It is observed that the deep representation learning method performs better than the classical method. Moreover, CFR performs better than the BNN due to the design of separate outcome prediction networks. Next is an out-of-sample case, which estimates IT of the unit with no observed outcome. It is evaluated on the test data set. An example of the out-of-sample case is that a new patient arrived and the goal is to select the best possible treatment. Similar result, the right table shows the result, and similar observations can be found from the table. Next, we introduce the second part of deep representation learning method, local similarity preserving based method. This kind of method are an extension of the balanced representation method, and the motivation is that the representation space should encode the following. First, in this new space, the treated and control group is balanced, which means as shown in the figure, the treated group and the control group have more overlappings, or they are more close to each other in the representation space. Second, this new space should preserve the similarity order information of the original space. Similar units shall have similar outcomes. Therefore, preserving the similarity information would benefit the outcome prediction. However, due to the first balancing goal, it is impossible to preserve all pairwise similarity information. Therefore, for different data points, the strength of the similarity should be the strength of the similarity preserving should be different. As shown in the figure, the similarity information of those pairs located in the margin area marked as a double arrow are more important and should be preserved. Based on this high-level idea, the site is proposed. Overall, site composes of representation network and outcome prediction network. To achieve the balancing and similarity preserving goal, 2 additional regularizations are added to the representation. In detail, for every batch, we select 3 important pairs and view the similarity information of those pairs are important. Therefore, we design the PDDM, similarity preserving regularization, to preserve the similarity information of those pairs. Meanwhile, to fulfill the balancing goal, MPDM, middle point distance minimization regularization, is designed to minimize the distance between the control and the treated group. Therefore, the loss function of the site contains 4 parts. The first part, LF, is a factual outcome prediction loss. The second part is the similarity preserving loss. Third part is balancing loss. And the last part is the regularization of the neural network parameters. Next, we introduce how to choose those 3 important pairs. We use a propensity score as a measure. The propensity score is defined as the probability of a unit being in the treated group. Therefore, through the definition, the propensity score can kind of reflect the locations of the unit. That is, if a unit's propensity score close to 0.5, then it will be located in the intermediate area of the treated and control group. If it is close to 0, then it will be located in the margin of the control group. Similarly, if a unit's propensity score is close to 1, then it is located in the margin of the treated area. So based on the propensity score, we first choose one pair located in the intermediate area, and then choose one pair of control units that is farthest from the selected intermediate pair. Similarly, we choose the farthest treated pair located in the treated margin. And the proposed PDDM aims to preserve the similarity information within and between those 3 pairs. Next is the MPDM, middle point distance minimization. The goal of MPDM aims to make makes the treated group and the control close to each other. In detail, we view the middle point of the 2 selected farthest control pair as a proxy to the center of the control group. Similarly, view the middle point of the 2 farthest selected treated pair as the center of the whole treated group. MPDM by minimize the distance between those 2 middle points to make the treated group and the control group gradually close to each other. Here is an experiment on the HDP and the job dataset. Compared with other methods, the site has better performance on IT estimation due to the balance and the local similarity preserving representation learning. Next is the experiment on the twins dataset. The twins dataset comes from the data of twin births in the USA between 1989 to 1991. It has total 11,400 twin pairs with 30 features related to their parent, the pregnancy, and their birth. The treated group is being the heavy twin, and the control group is being the light twin. The outcome is a 1-year mortality. In this dataset, the AUC of the outcome estimation is adopted as the evaluation metric. The right table shows the result, and similar observations can be found on this dataset. However, site has some drawbacks. Site only consider the similarity of string cases. Moreover, site requires that online data are spherically distributed when calculating the group distance. To overcome this, the ACE, an improvement of site, is proposed. Similar to site, ACE also obtains balanced distribution in the latent space. Different from site, ACE aims to preserve the fine-grained similarity information. The architecture of ACE is similar to CFR. To preserve the fine-grained similarity information, ACE imposes the balancing and adaptive similarity preserving regularization based on the applied on the representation R. The balancing is the same as what mentioned previously, and the adaptive similarity preserving explores all the pairwise similarity and similarity information and adaptively preserves those important similarity pairs. In detail, the balancing part of Bass regularization is the group distance between the treated and control group in the representation space. The other part is adaptive similarity preserving loss, which measures the similarity loss after representation learning by KL divergence. Well, Pij is the similarity between unit I and unit J in the original space, and Qij is the similarity between unit I and unit J in the latent space. This design can explore all the pairwise similarity information and avoid the additional data distribution assumptions. Here is an experiment on IHDP, jobs, and the twin dataset. From the table, it is observed that by adaptively preserving the fine-grained similarity information, ACE has better performance. Next, we introduce how to use representation learning to help estimate the treatment effect when the confounders contain the text covariates. Text type confounders are very common. For example, when we study the impact of different push platforms on the news reading experience. In this example, the treatment W is different platforms, mobile or computer. Outcome Y is a user reading experience. Confounder X is a news. It is text type data, which is not only affect the decision on what platform to push news, but also affect the user's reading experience. Another example is to study the impact of recommended item on user click-through rate or purchase rate. In this example, treatment W is recommended different items. Outcome Y is whether the user clicked or purchased. And the confounder X is the evaluation of the product or review of the product, which is text data. It affects whether the item is recommended to the user, and it also affects the user's purchase decision. This work aims to make the classical match method in causal inference applicable to dataset containing text data, so as to expand the scope of application of causal inference. The classical match method, as mentioned previously, finds the neighbors of the unit in another treatment group and uses the neighbor's factual outcome to estimate the user's counterfactual outcome. That is, if the unit receives another treatment, what the outcome would be. The classical match method cannot directly apply to text data because it is difficult for text data to fill out the near instrument variables using traditional feature selection method. First of all, what is near instrumental variables? As shown in the figure on the right, near instrumental variables refer to the variables that are more predictive to the treatment assignment W rather than the outcome Y. Existing researches show that when you are doing matching, taking into the near instrumental variables into account will amplify the estimation bias. On the numerical dataset, we can easily use feature selection method such as L1 regression to determine which variables are near instrumental variables. But when the data contains text type data, this method will no longer be applicable. In order to fill out information related to near instrument variables, the following game-based representation learning framework, CTEM, is proposed. CTEM is mainly composed of two parts, representation learning part and the treatment discriminator. Representation learning part input is a confounded X, output is a representation Z. The input of the treatment discriminator part is the representation Z and the outcome Y, and the output is the treatment assignment. These two parts play a minimax game. We think that if the representation learning part can successfully fool the treatment discriminator, then the output Z, output Z or the representation Z we get can successfully fill out the information related to near instrument variables. In the last step, we will do matching on the learned representation Z. The following is an experiment of CTEM on the news dataset. The news dataset comes from NY Times corpus with a total of 5,000 news items. The news in the treated group is pushed to the mobile, and the news in the control group is recommended to the desktop. Outcome Y is the user's reading experience, which is generated through simulation. The table on the right shows the IT estimation result of the proposed CTEM and the other baseline method. The blue box is based on the method marked as blue is based on the traditional feature selection method, and the green box is a classical matching method. By comparison, CTEM has achieved better results because it can fill out information related to the near instrument variables in the text data. On the previous method, all assume that there are no unobserved confounders. However, it is hard to verify that. Here, we introduce how to use VAE to handle the hidden confounders. The figure shows one example with a hidden confounder in the medical area. Z is a hidden confounder, such it is a social economic status. T is a treatment, which is a medication, and Y is the outcome, that is mortality. The observed covariate X is a noisy proxy of these, such as the income in the last year or the place of residence. Under the assumption that many proxies are available, CEVAE is proposed to estimate latent confounder using VAE. It discovers the hidden confounders and infer how the hidden confounders affect treatment and outcome. Overall, CEVAE requires weaker assumption about the data generating process and the structure of the hidden confounders. In detail, the left figure shows the inference network, and the right one is a model network. Here is the experimental result on IHDP and jobs dataset. By using the VAE to discover the observed confounders, the CEVAE have better performance. Next, let's introduce how GAN can help causal inference. In this work, the authors view the counterfactual outcome estimation as a missing label problem and capture the uncertainty in the counterfactual distribution by attempting to learn them using a game. The proposed method GANIT have two games. One is a counterfactual block, aims to complete the data, and the other one is ITE block to estimate the ITE. In detail, the input of the counterfactual block is a data with missing labels, and the output is a complete data. In this block, the counterfactual generator generates a counterfactual outcomes, and the counterfactual discriminator distinguishes which is a factual outcome given the combined vector of factual outcome and the generated counterfactual outcome. And the counterfactual block outputs complete dataset that is X, the covariance X, treatment T, and factual outcome and the generated counterfactual outcome. The second part is the IT block. The IT block is a regular game whose input is a complete dataset from the counterfactual block. In detail, the IT generator infers the potential outcome of the individual based on the complete dataset in a supervised way. The IT discriminator is a standard conditional game discriminator which distinguishes the potential outcome from the complete dataset or the IT generator. Next is the experiment on the HTTP twins and the jobs dataset. With a powerful game to capture the uncertainty in the counterfactual distribution, Gannett has the best performance. The previous three datasets are all binary treatments. The author also conduct experiment on the dataset with multiple treatments, which is constructed from the original twin dataset. It has 4 treatments with a combined of weight and the gender. The evaluation matrix is a mean squared error on the outcomes. The table shows the result, and Gannett still performed well on the dataset with multiple treatments. In summary, the deep representation learning for causal inference lies in 2 ways. One is a balanced representation learning, and the other is to use generative method to capture the uncertainty in the distribution of counterfactual or unobserved confounders. The drawbacks are that some methods lack theoretical guarantees, and they all require large samples to train.